Hello Paradigmers, welcome to week 10. This week we are going to be finally creating real Haskell programs that perform input-output operations such as reading or writing from standard I/O and files, and we're going to do that by introducing a new type class, the last new type class actually that we're going to talk about, called monad. And this type class allows us to perform effectful programming, that is to chain functions that produce effects like I/O side effects, while allowing Haskell to still be considered a pure language. So before we get there, let's quickly review the two base classes for monad, that is the two classes that all monads must also be instances of. That is functor, which it turns out we have been in effect using since the start of this course. Every time we've been mapping functions over some context, such as an array or a list, we have been treating those types as if they were functors, and then a couple of weeks ago we formalized that in Haskell, or rather we generalized it into a type class called functor, which guarantees that all instances of functors must have this fmap function available for them. And we've seen a bunch of instances of functors. We've seen eithers, we've seen lists, of course, we've seen maybe types, we have quickly looked at I/O. We've also seen that functions are instances of functor, as are tuples. There's some examples that we've seen before of common ways to map a simple function over different types of contexts. Then we introduced the applicative type class. Applicatives are also functors, but they introduce two more functions. The first one is a general way to take a value and place it into the context particular to that instance of the applicative, and then the applicative operator, which is another way of mapping a function, but this time it assumes that the function is also inside a context. Again, all of these different familiar types are instances of applicatives, and we've seen that the applicative combined with functor fmap allows us to lift binary functions over two contexts containing values. So here we are lifting times over two lists, and we see that because of the rules for applicative for lists, we finish up with the Cartesian product of all the ways to multiply the values in one list with the values in the other list. Here's another binary function, replicate, being lifted over a list of numbers, which become the first parameter to replicate, so the number of times to replicate, and then the second parameter comes from another list context of characters, and so the result is the characters replicated one time, two times, and three times. So in the workshop this week, we are going to be practicing reading and understanding and also writing Haskell types, and especially things like fmap, where we will be looking at actually some TypeScript code, and we will be comparing TypeScript code or rewriting TypeScript types into Haskell. So for example, if we consider the TypeScript type for the built-in array.map function, which takes a function that converts values inside the array to some result type and returns the set of results also inside an array. A direct translation of that TypeScript code to Haskell, assuming that we have some type class called array, would look like this. And so these are semantically identical with two type variables, t and u, and just following the conventions of the language, they become lowercase, and array, of course, becomes a type constraint, and otherwise, semantically, it is identical. So we've seen many examples now of how our old friends lists and types like maybe are instances of functor and applicative, providing a way to map functions over those contexts. We have also seen the IO type, but only in passing really before. However, it is also both functor and applicative. So if we think of maybe being a computation that can fail, and we think of a list as being a computation that can return 0 or many results, then I/O is a computation that somehow uses the outside world. So we might say that a value of type I/O(A) produces a value of type A while interacting with the outside world. That is, the I/O context comes from the side effect of interacting with the world. And we might also call this an I/O action or just an action. And the I/O is an effect. So some simple I/O actions are getLine, which reads a line of input from standard I/O and returns the result as a string inside an I/O context. The opposite, I guess, is putStrLine, which we've seen before, and takes a string and sends that string as output to standard I/O. And the return type is an I/O context, but with nothing in it. This open bracket, close bracket is also called unit, and it's similar to the void type, which we saw in TypeScript. It basically means that we have no value stored inside that I/O context that we care about. Another example of an I/O action would be getting the time from the system clock, and we could read a whole file from a given file path and return the result as a string in an I/O context. A point of terminology, so we say that the action, the I/O action of a putStrLine applied to a string is the whole application of the function to the string, not the function itself. It's also worth noting that values of type I/O(A) are proper values. That means that we care very much about the I/O context, and we have to work with care to access the values inside that context, just as we did for lists and maybes and other contexts. I can try out these actions in GHCI. So for example, looking at the type putStrLine, let's turn it into an action by giving it an argument. We see that the expression has type IO of unit, so it's an IO action. GHCI is going to recognize that it's an IO action and be able to execute it like that. That's fine. But how can I execute multiple of these IO actions in one expression? Well, I could put them in a list. For example, I could go putStrLine world. So now 2 IO actions in a list, but GHCI doesn't like it. The reason it doesn't like it is because if we inspect the type of this, we see that it is IO actions inside a list. GHCI really needs the IO to be on the outside of this type. So we have a problem where the type that we want is inside another context. Well, we recall from last week that we do have a function for reversing the containment order of contexts, and that is sequence. So now we are able to sequence the IO actions in this list to run one after the other. And that's fine, that worked. We see that the return type of these two, we see that the return type of this sequence over the list is a list of the units returned by each of these IO actions. So the effects of these IO actions are now elements in a new list. But what if we want one of these actions to depend on the result of a previous action? For example, what if we wanted to read some input from standard in using our other IO effect that we saw, IO action that we saw before, getLine. So getLine will prompt us to enter a string, and it reads the string from standard input, and that's the result, the string inside the IO context. But what if we want to sequence actions where a later action depends on the result of a previous action? What if we want to putstra-line the result of a getLine? And that's where the applicative runs into a limitation. So here's the problem with applicative. Let's say I want to read a person's name from standard IO using getLine, which is going to return that string inside an IO context, and then I want to greet the person. Here's a function that takes a string and prints it, prefixed by a nice salutation. How can I pass my IO string into a function that's expecting only a string? Of course, I do have a way from functor to map such a function over a IO context or any context, and that of course is fmap. So I can map greet over read name, and good, it's prompting me for a name, but nothing happened. What went wrong? Well, let's inspect the type of this expression, and we see that what we have is an IO, but then there's another IO action nested inside of it. So GHCI isn't doing the right thing. It's not executing this innermost IO. So we have these two nested contexts. Somehow we need to flatten them out. And there's really no way we can do that with functor and applicative functions only. We need something else. We need a new function that takes something, a string inside an IO context, and a function that expects just a string and returns a single IO context, and then somehow returns a flat IO context at the end. So there's our getLine or our readName function. There is our greet function. But what does it look like? Well, there is such a function, and it comes from the monad type class, and it's called bind. It's a binary operator, and you can see it expects some value inside a context, which looks a lot like our IO string. It expects a function that takes a value of the same type, but not in a context, and returns a different type inside the context, and then finally it does the thing of returning the result in only one context. And really, that's all there is to monads. There's a bunch of other functions built around bind, but the main innovation is this way of somehow flattening the nested results of operations that would otherwise return nested contexts. Here's some information about the monad type class. We can see that a monad is also an applicative, and therefore also a functor. We can see this new function, bind, that is really the key contribution of the monad type class, and some other functions that we'll talk about in a little while, and some we don't actually need. There's an interesting historical quirk of the Haskell type class system is that monad was actually invented before applicative, and as the type class evolved and became more finely grained, some things that were originally in monad became elevated to this new type class applicative. For example, return is now really just pure in applicative. As with applicative and functor, there are a bunch of things built into the prelude that are already monads. For example, lists are monads, maybes are monads, and IO is definitely a monad. So to recap once more this hierarchy of type classes for mapping, and now this new word binding over contexts, we have fmap with the fmap operator, which let us map functions over contexts like lists, and applicative, which is also a functor and introduced pure a way of putting values into the applicative type, and the applicative apply operator, which let us apply functions from inside contexts over values inside of the same contexts. And now we have monad, which introduces the bind operator. And you can see here we actually have a flipped version of bind, which is also defined in the monad type class. And the reason we're using that one here is because we see now there's a nice correspondence between the key functions defined in each of these type classes. They all allow us to apply functions in various configurations of contexts over values inside contexts. In our example of the flipped bind, we've simply composed the pure function with our little function that adds 1 to a number. And so that's now given us a function that has this type. So it takes a value and it puts it using pure into the monadic context. And so there's our function that has this type. In fact, it's taking a number and adding 1 to it and returning it inside. In this case, it's going to be the list monad. And the second parameter to the bind is the list. And the result, of course, is going to be the same as the results of these previous ones, which is simply a list of the numbers 2 through 10. 1 through 9 with 1 added to each. And you can keep in mind which one is which because of the nice graphics of the two operators. So the greater than signs point in the direction of the flow of values, if you like. So the regular bind takes a value on the left-hand side and pumps it through a pipeline into a function on the right-hand side, and vice versa for the flipped bind. And here they all are neatly laid out so that we can see the correspondences and also compared against our original way of applying functions to values using this dollar operator, so a bunch of different ways of applying functions in different configurations of contexts. There is also a super simple version of bind, which allows us to simply sequence actions when we're not interested in actually passing the values through. So for example, if I want to do 2 put-stroke lines one after the other, like so, then I can just find, using this version of bind, just greater than, which doesn't actually pass the value, any result of the previous one through. Let's look at the type of that operator, and we see that it takes on the left-hand side a value inside a monad context, and on the right-hand side also just a value on the monad context, and returns another value in the monad context. So what's the type of this thing up here? And we see it is just an IO of unit, which was the return type of this thing here. So this simple bind operator here, without the equals on the end, just sequences to IO actions like so. And here we have a similar little chain of actions to the one we had previously, except we've added a little greeting at the start that simply prints out a message. There is no result for that we're interested in, so we use the simple version of bind in order to then sequence the getLine action, which does have a return value, and then that gets passed through this regular bind to a function on the right-hand side. So these monadic chains get quite convoluted or quite long in Haskell quite frequently, so there's an alternative notation for it called do notation, and in fact I broke this down in the intro video for this week, but it's pretty straightforward. If you use do notation, then you can put each action on its own line, and the correct bind is used depending on whether a result needs to be passed through or not. If we need to take a result from a previous IO action. Then we use this assignment operator to put the value out of the monad context into a variable, and that is entirely equivalent to this chain of a bind into a lambda function like so. So instead of passing it into the parameter of a lambda function, it's passed the result of the get line into a variable there. One thing to note is the difference between assigning pure expressions to local variables using this let notation and the operator here to take values out of a monadic return type and into a local variable like that. I also showed a very similar example to this in the live coded intro for this week. There are a couple of other functions defined in the monad type class. We're going to see these in the tutorial this week. In fact, we're going to derive them and create instances for different types in the tutorial this week. The join one is very simple, and it is also very simple to understand and captures the essence of the monad type class very succinctly. It's a little bit like sequence. You can see, however, instead of flipping contexts, it flattens them. So on the parameter we pass into join is two nested monad contexts, and it flattens them into a single monad context. And once again, very easy to implement each of these using the regular bind function. An example of flattening with join on a nested maybe, and you can see it does that as you would expect. This operator is called Kleisli composition. I've also heard it called a fish because it looks kind of like a fish, and it is monadic function composition. So if we have two of these functions that the normal bind works over instead of just one, the Kleisli operator will compose them, and here is the simple implementation for the maybe type. So in conclusion, the monad is in many ways more of the same that we've been talking about with functor and applicative, just another way of dealing with contexts. In particular, it gives you an operator that allows you to squash nested contexts, which was exactly our join function that we saw at the end, and the bind function in general allows us to chain computations inside of contexts together. And where it really comes into its own is with the IO actions that we have been looking at here, and allows us to really handle them in a very type-safe way. So that's enough for now. We're going to get lots more practice with this in the tutorials and also in the workshop, and I'll look forward to seeing you there.